Good day, everyone. Uh, in our last meeting, we have discussed an introduction to reinforcement learning as well as the Bellman equation, which is a very essential equation when it comes to reinforcement learning. Also, we have discussed policy evaluation. So for today, we will discuss Markov decision processes and value iteration. Okay, so let's just say that this is the world of our agent. Our agent is this person right here that you can see. Okay, so this is our agent. And then these tiles are, let's just say, states. So in this state, the agent will get a reward, assuming this is 1. And then on this state, the agent will also receive a reward, assuming 20. Okay, so the agent can either go to this state or go here and then here. I know the agent can go here or go here, to either state. So if the agent goes to either of the states, the game will end, and the agent will get the reward that it has that's on that specific state. So this graphical representation of the world can also be represented in a Markov decision process. So, as I have said, the agent sees a treasure across a bridge and a coin behind the agent. Taking either the treasure or the coin will end the game. So, should the agent cross the bridge or should it walk away? So, as I have said earlier, this problem can be better represented in a Markov decision process like the diagram below. States are represented by circles. So, this is a state as land, and then this is another state as treasure and as coin. The terminal or goal states have double circles. So this means that this is a terminal or goal state. This is also a terminal or goal state because both of these have double circles. Then actions are represented by squares. This is an action. This is an action. So the agent can either cross the bridge or the agent can walk away. R is the reward taking that action. So if you go from okay, so let's say that you are in state in a land, then you decide to cross the bridge and you end up on the treasure. So that means that the action of crossing the bridge to get the treasure will result in a reward of 20. If you are in a land and you decide to walk away, and then you retrieve or you arrive at the coin state, that action will the action walking away will grant you a reward of 1. Okay. So now we want our agent to get the biggest reward. So we want to teach our agent to get the biggest reward. So of course we want the agent to go to treasure instead of coin, right? So how do we make our agent do that? So actually we can use the Bellman equation. Okay. However, we make some adjustments to the equation. So now, as you can see, we have added the max A or max action, which I will discuss in a while. So basically, the optimal value, I repeat, the optimal value of S is the action granting the maximum. Okay, so the action granting the maximum utility or value the um, of the succeeding state. Okay, this one. So we want we want to identify which of these actions, either cross bridge or walk away, results in the maximized value. Okay. Okay. Next slide. So first we calculate the. Wait for. Okay. So we replace the values. Okay. So we replace the values. So again, we have V optimal of S is equal to max action Gi- uh, given the reward of in state S, give performing action A and then transitioning to state S prime, plus our discount factor multiplied by the optimal value of the next state. So if we okay, let's go to the next slide. So we just replaced. So we actually just want to get the optimal value or the optimal action of this state sland. So that's why we plugged in sland here. Okay. So optimal value of sland is equal to max A R reward of sland given the action. So we have two actions here, cross bridge and walk away, and then S prime. So the S prime of cross bridge is S treasure. The S prime of walk away is S coin. Plus our discount factor multiplied by the optimal value of S prime. Okay, next. Next slide. So we just okay, now we calculate the values of each action of the state. Okay, we calculate the value of each of the state as land given each action, a cross bridge or a walk away. So these are separate. Okay, so these are separate equations. This one and this one, these are separate equations. Okay, so I want you to focus on this one first. Okay, focus on this first equation. Okay, so the value of SLAN when performing action cross bridge is the of reward of SLAN performing cross bridge transitioning to S treasure plus our discount factor multiplied by this is V opt the optimal value of treasure. Okay, so if we take a look, the reward of our SLAN cross bridge treasure is 20, right? So, okay, I'll just write here at the top. So this will be 20. Our gamma, so let's assume discount factor is zero point 0.9. Okay, so gamma will be zero point 0.9 plus zero point 0.9 times the value of treasure. So since this is the goal state, its value will be 0. Oh, not there. Times 0. Okay. So next, let's take a look at the second equation. So the value of S land when performing the action walk away is the reward of S land walk away S treasure. This is not S treasure. This is S coin. Apologies. This is S coin. Okay. S coin. Okay. This is also S coin. Yeah, it's S coin because we have no arrow leading from walk away to treasure, right? The arrow of walk away is to S coin, is pointing to S coin. So, okay, so what's the reward of S land walk away S coin? It is 1 plus zero point 0.9 times the value of V opt of S coin. It is 0 because it is a terminal state. So if we proceed to the next slide, you'll just see the same equation that I've written. Okay, so we have 20 plus 0 0.9, right? 20 plus 0 0.9 times 0. Then when you walk away, you have 1 plus 0 0.9 times 0. So next, okay. So now that we have calculated the values of S-land when performing each action, cross bridge and walk away. Which is the maximum? Is it 20 or 1? Okay. Again, so which is the maximum value? Is it 20 or 1? It's 20, right? So the value of optimal value of S-land will be the opt of S-land will be 20. Yeah. Okay, so that's just how simple it is. Okay. And then since crossing the bridge, the action of crossing the bridge is what gives the maximum value, then the optimal policy when you are in S-land is to cross the bridge. Okay, so the optimal policy is to cross the bridge. So, wala na siya. Next, next example. Okay, now we have updated our world. So in this example, we have, okay, we still have three, we now have three states, right? No, we have four. So we have this state, our S land. So this is S land. This is S coin. S coin. This is S treasure. Okay. Also, we have added another state. We have S crocodile. Okay. So what changed in this world? So aside from adding a new state S crocodile, this bridge can also break. So let's just assume that this bridge is very old. And because it is very old, it has a chance of breaking when the agent will step on it. So if the agent steps on the bridge and it breaks, then the agent will fall to a crocodile. When the agent falls into a crocodile, a negative reward will be given or the agent will be punished. However, if the agent successfully um, if the agent successfully crosses the bridge, then the agent will get the treasure. So okay, so the probability of so the so now we introduce probabilities. Okay, so now we introduce probabilities in our world. So the probability of the bridge breaking is P break is equal to zero point 0.3. P not break, P not break is equal to zero point 0.7. So this just means that there is a 70%, okay? There is a 70% success rate or 70% chance that the agent will successfully cross the bridge and get the treasure, and there is a 30% chance that the agent will not get the treasure because the bridge will break and the agent will fall into our crocodile. So we can represent it in another Markov decision process. All right. So I just added this one. Just added this one, and also added probabilities. So okay, focus here below. The probability, the probability of going to S coin when you walk away from S land is 1, meaning there's a 100% chance that you will successfully get the coin when you walk away. However, if you look at the top, if you decide or if the agent decides to cross the bridge, there is a zero point 0.7 probability that when crossing the bridge, the agent will go to the treasure. There's also a zero point 0.3 probability that the agent will go to the crocodile. Also notice that the reward when the agent falls into a crocodile is negative 50. Oops. Okay. Okay, next slide. So let's update the previous equation to account for probabilities. So what I just added here is, okay, what I just added here is this probability, probability of um, transitioning from S to S prime given the action A, okay, times or multiplied by the expected reward from that action, okay. So let's just say, for example, yes, in the crocodile. So you have a zero point 0.3 probability, right? So we just multiply zero point 0.3 times the expected reward of this path. Okay. Another thing, we also multiply zero point 0.7 to the expected reward of this path. After we multiplied each, so this will have different values. So now we have two values. We just add those two values afterwards. So this is why I have summate this to the function. Just add those two values under, okay, under this action, under one action. Okay. After adding those values, that the resulting value or the summated value will be the value of SLAN given when performing that action cross bridge. Okay. So next slide. Okay. So of course, our equation, the optimal value of SLAN is equal to the maximum. Okay. So this is lacking. Sorry, I missed things. So we have max A summation of S prime P S A S prime times, okay, the address, okay, times this, the one in brackets. Okay. Okay. Things are getting more exciting. So yeah. So we first okay, so the we have two different equations here. We have this equation, we have this equation, and then sort of this equation for each path. So we have this path, right? We have this path, we also have this path, and we have this path, right? Okay, so each path is represented by different equations. Okay, so it looks like that the first equation corresponds to this path. Okay. Oops. Okay. So the first equation corresponds to this path. So what is the probability of SLAN cross-bridge treasure? SLAN cross-bridge treasure. So it is zero point 0.7. So we have zero point 0.7 times, okay, what is the reward of SLAN cross-bridge treasure? So the reward of SLAN cross-bridge treasure is 20, right? So 20 plus gamma. Our gamma is zero point 0.9. Let's just assume. Just assume that our gamma is zero point 0.9. And then um, what is the optimal value of treasure? This is 0 because the optimal value of treasure is 0 because it is a goal state times 0. Okay, next. You know what? I'll just write it here on the left side. 0.7 times 20 plus 0.9 times 0. Okay. The next equation refers to this path. Refers to this path. So what is the probability of S-land cross-bridge crocodile? S-land cross-bridge S-land cross-bridge crocodile. It is zero point 0.3. 0.3 times reward of S-land cross-bridge crocodile is negative 50. So negative 50 plus our gamma, which is zero point 0.9, times the value of S crocodile. So the value of S crocodile is 0 because it is a goal state. Okay, good. After that, we proceed with the calculation of the third path. Okay, the third path. Oops, what happened? Okay, third path uh, refers to being in Estland and then walking away, which leads to coin. So the probability of Estland walk away coin is 1, right? Times reward of Estland walk away coin. Reward is 1. So 1 times 1 plus gamma zero point 0.9 times the value of S coin. The value of S coin is 0 because it is equal state. Next. Okay, things right. Okay, next slide. This one will not up. Okay. So yeah, if you take a look here and here and here, it's just the same as to what I have written in the previous slide. This one. Okay. All right. So notice that I have added. Okay, I have added the value of this path and the value of this path. Notice it's because we want the summated weighted value of this action. That's the reason why we have added those two. Next slide. Okay, so now after evaluating the equation in the previous slide, we have come to these values. So the value of crossing the bridge is negative 1 and the value of walking away is 1. So which of the two is largest? Is it negative 1 or 1? Again, which one is the maximum value? Is it negative 1 or 1? So yeah, it's obvious. The maximum value is 1, right? So this tells us that if the agent is in S land, it is now better to walk away than to cross the bridge. So it's basically telling the agent that it's not worth it. It's not worth it to cross the bridge. It's better to just walk away and get the sure reward of 1. Okay, so this x, this will be the path that our um, um, agent will take. So next example. So now we have, so now we have updated our um, world, right? So we have added this. So we have added this. So this one is another state. Let's just call it SLAN2. SLAN2. And then this is still crocodile S crocodile. This is also S crocodile. So notice that we have two bridges now. This bridge has a P break. Okay, the probability of breaking this bridge is zero point 0.3. However, this bridge right here, it has a probability of breaking of zero point 0.1. So this means that this bridge, okay, the new bridge is sturdier or more reliable than the older bridge. So should our agent take the older bridge or walk away or go around and take the sturdier bridge? However, take note that the reward when the agent goes in this or when the agent goes around is -10. Okay, so we're also going to take that into account. So that again, the reward of going around to this state is -10. So again, we can represent this as a Markov decision process. Okay, so we can represent this as a Markov decision process. So I just moved this. I just moved this from the bottom to the left side and added this one. I just added. No, I added this one. Okay. So this represents the extension of the Markov decision process. Just extends the older MDP that we have created. I added the go around action, which transitions to SLAN2. Then when you are in SLAN2, you only have one action, which is to cross the bridge. When you cross the bridge, there is a zero point 0.1 probability of go, falling down to the crocodile, and then there is a zero point 0.9 probability of actually arriving to the treasure. Next slide. So again, we update our previous equation to allow the back propagation of values. So notice that we have added t. Okay, we have added t. So the t signifies time. T signifies time, which is the current iteration of the values. With enough time, information from the goal states can be propagated backwards to return an optimal solution. This process is also known as value iteration. So basically, the algorithm of value iteration is just to repeat and repeat the process of calculating the values until until the values do not change anymore. So that's what we call the convergence, which I will show in a while. Okay. So for the first iteration, or at t is equal to 0, at t is equal to 0, we initialize the values to 0. So what do we mean by initializing the values to 0? So remember that we have 1, 2, 3, 4, 5 states, right? One state, second state, third state, fourth state, and fifth state. So the values of these states at time is equal to 0 is equal to 0. So it's one right here. So set all the values of all states to 0 at t is equal to 0. So after that, after we have calculated t is equal to 0, we will now calculate t is equal to 1. Yeah, calculate the values at t is equal to 1. So first, we calculate the optimal value of S-1 at t is equal to 1. By the way. So, okay. Um, the goal states or the states with two circles, their values will be 0 all throughout the time. Okay. However, the value of the states that are not final states will change depending on how the values are being propagated. Okay, so basically, the values that we're just going to calculate is this S1 and S2. So again, we will calculate the values of S1 and S2 only. All right. So again, calculate the values at t is equal to 1 of S1. So, yes. Um, okay, so this equation is lacking. Remember, remember we have the probabilities, right? So the probability of SAS prime times the sum, or I mean the expected utility of, yeah, this. Okay, so you know the drill. We calculate the value of, yeah, this one. Okay. So we now have four equations. Okay, because we have four paths. Yeah, right. We have four paths. We have this path here. We have this path here. We have another path here. And lastly, we have this path. Right? Okay. So, yeah, I'll just erase it for now. Okay, so first we calculate the value of this. So the values probability of S is S than 1. Okay, S is S than 1. A is equal to cross bridge. And then to treasure. So that is 0.7. 0.7 times the reward of S-1 cross bridge treasure, it is 20. Plus gamma, assume it's zero point 0.9, gamma is zero point 0.9, times the optimal value at t is equal to 0 of treasure. So what is the optimal value of treasure at t is equal to 0? So if we take a look at the table on the right side, it is 0, right? So multiply it by 0 times 0. Okay. Next, we calculate the value of S-1 crossing the bridge and transitioning to crocodile. So probability is 0.3. 3 times the reward of negative 50 plus zero point 0.9, which is our gamma, times v optimal value of crocodile, as crocodile at time is equal to 0. It is equal to 0. Next. Uh-huh. Okay. Next, we calculate the value of this path. So what's the probability? The probability is 1 multiplied by the reward of 1 plus gamma of zero point 0.9 times the value, optimal value of S coin at time is equal to 0, which is basically 0. Lastly, we calculate the path, the value of this path. So given the action go around, what is the probability that you will land at SN2? It is 1 times the reward, which is negative 10 plus zero point 0.9 times the value of SN2 at time is equal to 0. So it is 0. Mhm. Okay, so it looks, I think, what I've written is correct. So let's proceed to the next slide. Okay, next slide. So yeah, it's basically just the same from what I've written in the previous slide. These things. Right? So remember that we add these two things. Okay, we add these two things because they are in the same action. We just want one value for cross bridge. So after we evaluate these equations, we are given these values. Okay. So which one is the maximum? Negative 1, 1, or negative 10? So obviously the maximum value is 1 and the action is walk away, right? So in the right side of our in the right side in our table, we write 1 and we also write walk away. So this tells us that walk away provided the highest value for s than 1 at t is equal to 1. Okay. Next, we calculate the value of s than 2. Calculate the value of s than 2 at t is equal to 1. So yeah, you know the drill. Summation of E S E S prime times X. Okay, so yeah, we have two paths. First, we have this path, and then we have this path, right? So, okay, so what's the probability of going to the treasure when you're in S2? It is 0.9. 0.9 times the reward of is 20. 20 plus gamma of zero point 0.9 times v opt of S treasure at time is equal to 0, which is 0. Then below we have, yeah, the crocodile path. So what's the probability of going to the crocodile when crossing the bridge at S92? It is 0.1. times the reward of negative 50 plus 0.9 times 0. Next slide. Yep. Okay, so correct. That's correct. So if we evaluate the equation, we get 13 cross bridge. 13, 13 cross bridge, cross bridge. Okay, next. Yeah, so we just set the values of S threshold, S crocodile, and S going to 0 at t is equal to 1 because they are final states. Next, calculate the values at t is equal to 2. So, okay, so we have finished calculating the values at t is equal to 1. Next, we have calculated the values at t is equal to 2, right? Okay. So we just repeat the process. Calculate again the optimal value of the SLand 1 at t is equal to 2. Okay, next. So what's the probability of um, going to the treasure when crossing the bridge? It is 0.7. Reward is 20. Gamma of 0.9. Okay, so notice that, okay, wait. So take a look here. Take a look here. So notice that t is now equal to 2, right? And then here t is equal to 1. Okay, so this is where the back propagation, where you can like see the back propagation. So we basically look back to the previous value of the treasure, okay, or of the state. So let me just erase it. So what is the optimal value of treasure at t is equal to 1? It is 0. Okay, so this is just 0. Easy. Next. What is the probability of going to the crocodile when crossing the bridge at S line 1? It is 0.3. Reward is negative 50 plus zero point 0.9 of gamma multiplied by the value of S crocodile at t is equal to 1, which is 0. Okay. Next, we calculate the value when walking away. So what is the probability of going to the coin when walking away? It is 1. The reward is also 1. Okay, reward is 1. Gamma 0.9. Um, optimal value of S coin at t is equal to 1 is 0. Okay, next. If we go around, of what's the probability of landing or arriving at S land 2 when going around? It is 1. The reward is negative 10. Gamma is zero point 0.9. And, okay, so this is where things get a little bit exciting. So, um, so V opt, okay, optimal value of S land 2 at t is equal to 1 is not 0. It is 13. So we write 13. Okay, so if we go, let me just fix the equations real quick. Times plus. Okay, so that's how the equations will look like. So if we go to the next slide, it will just be the same. Um, okay, yeah, so it's just the same, right? Okay, so it's the same. So if we evaluate these the values, we get this result. So now the value of SN1 at t is equal to 2 will be the maximum uh, value of these, which is 1.7. 1.7. And then the action is go around. So now we update t is equal to 2 of SN1, value of SN at t is equal to 2, 1.7. And then the action now is updated from walk away, it now changed to go around. Okay, so next. We calculate the value of SN2 at t is equal to 2. Okay, so yeah, what's the probability of arriving at the state treasure when crossing the bridge? It is, yeah, zero point 0.9. 0.9 times the reward. Reward is 20. 20 plus gamma of zero point 0.9 times V opt at T1 of treasure is 0. Okay. Then below we have probability of arriving at the crocodile when crossing the bridge. It's zero point 0.1 times reward of negative 50 plus zero point 0.9 times optimal value of S crocodile at t is equal to 1, which is 0. So it results in this value. Crossing the bridge is equal to 30. Okay, so the maximum value is 13 and the action is cross the bridge. So notice that SN2 did not change. Right? It's still the same, 13 and cross the bridge. Also, we set the values of treasure, crocodile, and coin to 0 because again, they are goal states. Okay, so we repeat the process again at t is equal to 3. Okay, however, I will not show it anymore, but basically when we calculate the values again at t is equal to 3, the values will not change anymore. So basically at t is equal to 3, the value of SN1 will be 1.7 with the action of going around. The value at SN2 is also 13 when crossing the bridge, okay, at t is equal to 3. Therefore, because the values have not changed at t is equal to 3, we have reached convergence. So because we have reached convergence, we have found the solution of our um, we have found the solution to our MDP. So yeah, therefore the best policy at SLAN1 is go around. The best policy at SLAN2 is cross the bridge. Okay, so I hope that's clear. Okay, so here, let me show you something. So here I made a simple web application that represents the grid world and also um, value iteration. Okay, so yeah, as you all know, squares here below represent the states. Okay, the squares represent the states. Um, the green ones are positive rewards. The red ones are negative rewards. Also, when you arrive at these red and green states, you can see my mouse. Where's my mouse? Let me just close the okay, there it is. Okay, so again, yeah, this is a grid world. Each square represents a state. The green squares are positive rewards, the red squares are negative rewards. And if the agent arrives at either red or green squares, the game will end. Okay, so what we want to do, we want our agent to learn. Um, we want our agent to learn basically. We call that how to maximize the reward in the long run. Okay, we want our agent to learn to maximize the reward in the long run. So let's just say that. Let's make pen. Okay, anyway, okay. So yeah, disregard this just right now. Okay, don't mind this right now. So let's just say that our discount factor is 0.9. Then yeah, let's just say that our discount factor is zero point 0.9. Also, by the way, these small squares, these inputs here are the rewards if you reach that state. Okay. So for example, if you let's just let me try another browser. I'm trying to find Microsoft Edge. Okay, there it is. I think it is an in feature. Uh, do you have an in feature? You know what? Never mind. Let's just go back to my favorite browser, Opera. Okay, so let's just say that you're in this state, the upper left state, and your agent goes down. So basically, your agent will receive zero reward. Okay, okay. What if your agent is in this state? Okay, this the one in blue. The you can see here the blue something. So what if your agent is in that state, and then it goes down? So after going down, your agent will receive a reward of 2, and the game will end. Okay, so that's just how things are represented. Also, the V, okay, V is equal to something that is the value. That is the value of that state at the current iteration. Okay. So now let's try simulating um, the values. Okay, I mean the value iteration. So I'm I think so, okay, by the way, the actions that are allowed are only up, down, left, right. If you go to the edge when performing any action, you will just go back to the state that you are in. Okay. So if I click iterate, the values should update at t is equal to 1. Okay. So basically what you're looking at right now is t is equal to 0. If I click on iterate, we will see t is equal to 1. So I think this will be 20. This will be 20. Okay. This will be 2, and then this will be 2. The other things will be 0. Okay, iterate. Okay, great. So I was correct. This will be 20, this will be 2, and this is also 2. Also, notice the policy at this state is down. So this tells us that if you're in this state, it is best if you go down. Also in this state, if our agent is in this state, it is best if it goes left. Okay. However, here uh, the actions are either up, down, or left. So notice that there is no right because yeah, the value here is yeah, you don't want to go here because the reward is negative 50. Okay. Basically, if you go to the right side, the value will be negative 50. However, if you go up, down, or left, the value of this state will be 0. So that's why, yeah, they have the same values. These actions have the same values. Okay, this one, yeah, down. If you're in this state, yeah, it's best if you go down. Okay. So next, we iterate at for t is equal to 2. I'm assuming the value of this will be 20 times zero point 0.9. The value of this will be The value of this will be 20 times zero point 0.9. The value of this will be 2 times zero point 0.9. So I guess 1.8. Is that correct? This will be also 2 times 1. This will also be 2 times zero point 0.9, which is equal to 1.8. Let's see if I am correct. Yep. Okay, I am correct. Okay, you can see here. This is 18. This is 1.8. So notice also that the policy have updated. So instead of going down and right, this has changed to just down. So this one, instead of going up, down, left, this is it. The policy at this state has changed to just down and left. So this also just changed just to down. Okay. Next, iterate for t is equal to 3. I think this will be 18 times zero point 0.9. Yeah, this will be 18 times zero point 0.9. This will be 1.8 times zero point 0.9. So, okay. Yep, I was incorrect again. So it changed to 16.20. This is 1.62. The value here also changed to right. I mean, the policy here changed to right. Because the best action to do when you are here in this state is to go right. However, this is still down, and this has changed to down or left. Yep. Because, yeah, the values here are equal. So, what will happen if we iterate again? So, uh, I'm predicting that the value of this will change. Okay, the value of this will change to 16.2 times 16.2 times zero point 0.9. And then the policy here will become right. So if we iterate, okay, I was right again. If we iterate again, if we repeat our iteration, this will become 14.58 times zero point 0.9. This will become 14.58 times zero point 0.9. And the policy here will be right. The policy here will be up. Okay, let's see if I'm correct. Okay, right, and then up. Next. How about this one? Okay, so I'm predicting that the value here will be 13.2 times zero point 0.9. The value here will be 13.2 times zero point 0.9. And also the policy will be up. The policy here will be, I guess, up and left. No, up and right. So iterate. Yep, I'm correct again. 11.81, 11.21. And then up, and then this one, up and right. So yeah, if we do our next iteration, nothing happened. Click again, nothing happened. Nothing happened. I'm just clicking, clicking, clicking. Nothing happened. This tells us that we have reached convergence because the values have not changed. So again, we have reached convergence because the values have not changed. Okay? So yeah, that's just how simple it is. Propagating backwards. Okay. Okay, so I have reset the board. Okay, so I have reset the board. As you can see, the rewards here have become back to zero. And then the values have also become back to zero. So now let's introduce the slip probabilities. So now we will have probabilities. So the slip probability is basically the probability that the agent will take a random action that is against your current action. Okay. So for example, you are in this state. Okay, you are in this state, and then your agent decides to act or to perform the action down. Okay, so if your agent tries to perform the action down, um, there is a probability that the agent will not go to this state. So there's a probability which we will call the slip probability that the agent will instead take left, right, or up. Okay. So again, so again, let's assume that you are in this state and your desired action is down. Okay, your desired action is down. However, um, instead of going down, there's a zero point 0.1 probability that your agent can go to the state, can go back to the current state, or go to the state on the left, or go to the state on the top. Okay, so we call that the slip probability. So let's just say that the slip probability is zero point 0.1. So if the slip probability is zero point 0.1, there is a 0.9%, there is a 0.9 probability that the agent will go down if you want it to go down. And then there is a 0.1 probability that the agent will go to either left, up, or the same state if you want it to go down. Okay, so it's a bit confusing, but yeah, it's a bit confusing, so I'm just gonna repeat one last time. So there is a zero point 0.9 probability. So basically 1 minus zero point 0.1. Okay, there's a zero point 0.9 probability that the agent will go down if you want it to go down or if you desire it to go down. And then there is a zero point 0.1 probability that it will either go to the left, up, or the same state. Okay, so now let's try to calculate the values with a zero point 0.9, zero point 0.1 slip probability. So iterate. Okay, all right. So the values didn't change anymore, right? So it looks like, okay, it looks like uh, the solution to this MDP or this problem is to go um, to the reward that has the value of 20. Okay, to the goal state of 20. Okay, so if you are okay, so for example, you are in this state. If you are in this state, the if you are in this state, the agent is being told to go up, up, right, right, down, down. Okay, the agent is in this state, it is told to go up, right, right, down, down. If the agent is in this state, up, 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 right, right, down, down. Okay, notice. Okay, I want you to notice something. So notice that the agent in this state will go up only. It will not go to the right. Okay, okay. So again, notice that at this state, the agent will just go up. We do not have a go right. We do not have a go right action here. Okay. It's because if the agent goes to the right, you increase the risk that it will slip into the punishment. So that's a bad thing. So we have just taught our agent to avoid the tiles where it will most likely be punished. So those tiles are this tile and this tile. Okay, so we have taught our agent to avoid these tiles. However, there is no avoiding this because this is the only way to arrive at this state. Okay. Okay, so let me reset again. So what if we increase our slip probability to 0.3? So let iterate, iterate, iterate. Hey, things have gotten more interesting. So now, as you have noticed, if the agent is in this state, the best policy is to go right, right, okay? And then if the agent is in this state, it's best to go down. If the agent is in this state, it's also best to go down, okay? However, if the agent is in this state, it is best to go left, and then down, and then down. If the agent is in this state, it's best to go left, and then down. In this state, it is best to go left. So now, by just increasing the slip probability, we have taught our agent to avoid the bigger reward if they are in a certain state. So if the agent is in this state or in this state, oh wait, if the agent is in this state, this state, this state, this state, or this state, we have taught it to avoid the 20 reward. So it should instead take the reward of 2. However, at this state, and this state, it looks like it is best if our agent takes the reward of 20. Okay, so yeah, let me just refresh again. So let's just try a slip probability of zero point 0.1 again. So let's just go back and then change the discount factor to zero point 0.5. Yeah, I'm just curious what will happen. Okay, so iterate, iterate, iterate. Oh, interesting. Okay, so interesting. So now that the discount factor is smaller, um, these states, okay, this state, this state, this state, and this state will go to the reward of 20. However, this state, and this state will go to the reward of um, 2. Very interesting. Next. Yeah, okay, so that's all, I guess. I'm not going to give any other examples. I think it's enough. So yeah, yeah, it's very interesting. These things are very interesting. Okay, so let me show you another thing for a while. This is a YouTube video that I like about, yeah, this is basically my primary reference uh, for this lecture.
Is expected utility.
Okay, yeah. Okay, so this video by Stanford Online, it's titled Lecture 7, Markov Decision Processes, Value Iteration, Stanford CS221 AI, Autumn 2019. So I suggest that you take a look at this one and yeah, just watch it. So I hope that by giving my lecture first, you will have an easier understanding of um, this video by the Stanford Online. Okay, so yeah, just please watch this and review. You can also watch other videos. So I hope that the other videos that you will find online will also be, I guess, easier to understand after my lecture. Okay, Um, yeah. So I guess that's all. Thank you for watching. So yeah, this is my resources. So thank you everyone. Goodbye.